time to dive into some conservation of momentum problems, angular momentum that is. So let's do it. Let's start with a door that's swinging from a hinge. Now this is a view from above. So we have this door and it's hinged here. There's the doorknobs. We got a 10-gram bullet that's moving at 400 meters per second that's going to embed itself into the door. The width of the door is 1 meter. We're looking down again. Half a meter from the pivot point, the bullet is entering the door. So there it is. And the question is, what's the angular velocity after the bullet hits the door? Well, angular momentum before is angular momentum after. After is equal to before. So we're looking for the after, because that's where the angular velocity will be contained. So it's linear momentum times the perpendicular radius. And that's going to be the mass of the bullet times its velocity times the perpendicular radius from the pivot point, the point in question here, which is a half a meter. So when you do this multiplication, you get 2 kilogram meters per second. Well, so L prime is I omega. So we're just going to solve for omega. So first of all, let's get I. I is the moment of inertia of a door pivoted from one end, plus the moment of inertia of the bullet pivoted from that same point. So the bullet's a point object, but it's not very massive. So here it is, embedded in there. So it's the moment of inertia of the point object plus the moment of inertia of a door pivoted from one end, which is the same as a thin rod pivoted at one end. That's the 1/3 ml squared formula, plus ml over 2 squared, little m. All right, so that's 5 kilogram meters per kilogram meter squared, plus a very little 0.0025 kilogram meter squared. So omega is simply L prime over I, 2 over the 5.0025, gives us 0.4 radians per second. So it's a really straightforward application of the concepts of angular momentum. Let's do another angular momentum problem that seems more directly angular in its nature, because it'll be two rotating disks coming together. Here's disk 1, I1, omega 1, so spinning in that direction. Now we're going to bring in another disk, I2, and it's rotating at omega 2, so it's rotating the opposite way that this one is, and it has a different moment of inertia. And we're going to let these two surfaces come together. This is kind of like a clutch. This idea of a clutch on a car, where the flywheel and the pressure plate on the transmission basically brings the engine to the transmission and transfers power from one to the other. So there it is. We bring disk 2 and disk 1 together. So this is really an angular collision. So when they collide, for each pair of points that are in contact between the surfaces here, the following is true. The force of particle 1 on 2 is equal to negative the force of particle 2 on 1. It's just Newton's third law. That's all that is. Now it's the same radius vector from the center of mass axis, which goes right there. So from this center mass axis, wherever that point is on one disk, the counterpoint, the corresponding pair for that point, which is in contact with it, is what we're talking about. And there's an unlimited number of possible points in contact. If you multiply through by r, then it's the same r, same magnitude, same vector, same scalar, or same magnitude of that vector, is f1 and 2r is equal to minus f2 1r. Sum over all the points, and you have the actual torque. Torque of 1 on 2 is equal to negative torque 2 on 1. The time during which these forces interact is the same by definition, so multiply by delta t. But torque delta t has got a special name, and it's called angular momentum, or change in angular momentum particularly. So specifically, delta L1 equals minus delta L2, which is also a definition of the angular impulse of one being the negative of the angular impulse on the other. An angular impulse is related to the change in angular momentum. I1 delta omega 1 is minus I2 delta omega 2. Now the moments of inertia are not the same, but these are kind of like two masses. Unequal masses, but they come together. So now the total angular momentum before is I1 omega 1 plus I2 omega 2. That's the total angular momentum. And afterwards, it's the combined moment of inertia times the new angular velocity, because that's the same for both of them at this point. Yes, that probably should look familiar. This is an inelastic collision. They're colliding inelastically. The torques are always equal and opposite during the collision. Given that being the case, we can say the rate at which the angular momentum of the first one changes is plus the rate at which the angular momentum of the second disk changes, which is the definition of torque on one plus torque on the other, is equal to 0. The combined torque is equal to 0. Let's now check out a very interesting conservation of angular momentum scenario. You might remember a system like this that we did a lab, spinning a stopper through a glass tube with the mass hanging down. Now we know that as this mass goes in circular motion at an angular velocity omega 1, it's also got a moment of inertia, I1. It's a point mass at radius r from the axis of rotation here. And then what we can do is apply an external force. When we apply this external force, basically what that does is pulls this in, reduces the radius. And you may or may not recall what happens. Well, we are equipped to specify exactly what happens here. So as we pull this down, we have a new R2, and we have a new I2 as well, right? Well, if the sum of the torques equals 0, now pause, is any torque being applied to this mass? The only thing we've done in pulling this down over here is cause the string to go in. That's pulling inward. Now torque needs a radius through a force. That line of action, the force, is passing right through the axis of rotation. So therefore it's not applying any torque. So there is no torque, as a matter of fact. And therefore, that's dl dt, the rate at which angular momentum changes, which is the definition of torque, it's now 0. So the angular momentum is constant. So we've established that the angular momentum is constant. Now don't let this escape you too quickly. This is a very important type of concept. Something spinning in a circle, we pull inward on it. The one thing that we don't do is apply a torque. If you don't want to apply a torque, you don't change the angular momentum. So the momenta are the same in the two scenarios. I1 omega 1 is I2 omega 2. But of course the i's are different. So that tells us that the omegas are going to be different as well. This is something that we can actually do. We can place ourselves on a spinning disc, chair, or a platform. Take a couple dumbbells, hold them out, and when we pull them in, something interesting is going to happen. First of all, we get spinning up at angular velocity omega, radius r. And then as we pull these in, and we see a smaller radius as we spin around now. Kind of like well, exactly like a skater pulling in her arms and legs. Now our omega, by definition, if you look at this, the I2 has just gotten less because we've taken the mass and reduced the radius. Therefore, omega 2 has to go up at the same time. So, the kinetic energy is 1/2 I omega squared. Well, what happened? When the dumbbells are pulled in, was there any external torque? There was no external torque, for the same reason that there was none up here. Because we're pulling directly in, we're not putting a force through a radius arm, perpendicular to a radius arm. So what happens to the angular momentum? The same. Nothing happens to it. What happens to kinetic energy? Does it stay the same? we'll have to check that out. Well, let's check out the kinetic energy of the two objects. K1, 1/2 I1 omega 1 squared. K2, 1/2 I2 omega 2 squared. And from conservation of angular momentum, we have that I1 omega 1 is I2 omega 2. So we can solve for omega 2, I1 omega 1 over I2. So we're going to take this and sub it in for K2. We'll sub it in there and then relate the kinetic energies and see what happens. So K2 is 1/2 I2 omega 2 squared. That's 1/2 I1 squared omega 1 squared over I2, because one of the I2's canceled. And so we have the ratio of K2 over K1, the new K2 we just got over the K1, which is here. That all cancels.
Wow!
And we get I1 over I2 is what K2 over K1 is. So the ratio of K2 to K1 is the moment of inertia of 1 to the moment of inertia of number 2. So it's like inversely proportional, the kinetic energies. Why is this? Well, I1 is larger than I2. Right? The mass was spread out more. The energy is then, means energy is added to the system. Right? So energy had to be added to the system. And how does it get added to the system? Well, in fact, I mean, like, where does it come from? Well, if you think about it, as you had those dumbbells, you actually had to pull them in. So you, spinning around, had to do work on those dumbbells to get them come in. So the arms do work, and that increases the kinetic energy.
How about a little problem where we conserve rotational momentum, as always, and we lose some kinetic energy? That should be fun.
Well, indeed, that should be fun. So let's get on with it. Here's disk A and disk B coming together. Disk A, moment of inertia A, spinning at omega 0. And disk B, twice the moment of inertia of disk A. So basically just twice the thickness. Very simple. This clutch that's going to be responsible for the angular collision has negligible moments of inertia. Kinetic energy of A is 1/2 IA omega 0 squared. Now it says, the problem says that 5,000 joules of heat is developed. So what's the original K of this disk? Well, it's 1/2 IA omega 0 squared, which is 1/2 of IB over 2, because that's IA omega 0 squared. Now that's equal to what it is afterwards plus 5,000, because I said we're losing 5,000 joules to heat. So what's available after is diminished by 5,000 joules. Conservation of angular momentum, nothing is lost. L is equal to I omega, and that's going to be the same angular momentum afterwards. What it says is that IA omega 0 is IA plus IB. Basically, you're combining the rotational masses, the moments of inertia, with the new omega prime. So omega prime is IA omega 0 over IA plus IB. But IB is twice IA, so it's IA omega 0 over 3IA. Thus, the angular velocity after the angular collision is 1/3 omega 0. So the moment of inertia of the first disk is omega 0 IA. Keep that in the back of our minds. As we solve for K prime, the kinetic energy after the collision is 1/2 IA, 1/2 of the moment of inertia, which is 3 IA, okay, because it's 1 plus 2, times the angular velocity in terms of the original, omega 0 over 3 squared. Well, if you look at it, this quantity here has a Ka that factors out. 1/2 IA omega 0 squared factors out of it. There it is. and we get 1/3 Ka, so that's K prime. Thus, Ka equals K prime, which is 1/3 Ka, plus 5,000. So K prime, 1/3 Ka, K prime plus 5,000. There it is. But Ka is not 1/3 Ka, it's 3/3 Ka. Therefore, 2/3 Ka is 5,000. And we get our coveted result that Ka equals 7,500 joules.